Okay, well, good evening, everybody, and welcome to the Department of Chemistry. This lecture, then, we are looking at Group 1 of the periodic table. Now, of course, everything around us is made up of the elements, and there are many elements. So here are a few elements. So we have, for instance, there's oxygen, of course, aluminium, calcium. All these are common elements, carbon, nitrogen. But there are many, many elements. We're going to be here quite some time at this rate. There's over 100 different elements. Here they all are in some rather random order. Remember, these make up everything around us in some form or another. How can we make sense of all these elements? Well, the first person that did this, that actually made some sense of the different elements, was this chap, Dmitry Mendeleev, a Russian. And he first proposed the periodic table of the elements. And this is our starting point for today. We're going to be looking at one family of elements within the periodic table, or a group. We're going to be looking at group 1. Now, this is the red group coloured here. Maybe hydrogen at the start, then lithium, sodium, potassium, rubidium, and cesium. So Mendeleev arranged all the elements in order of, well, he arranged them in order of increasing atomic weight. That's not quite how it should be, but that's not quite the real point of the periodic table, as we shall see shortly. But he also, this was his key stroke of genius, arranged them into groups with related properties. And the groups are shown vertically like this. So this is group 1. We have group 2 here, another family with similar properties, group 3, or 13, 14, 15, 16, 17, 18. These ones are the noble gases, for instance. All of these are gases. So within each group, they have similar properties. We sort of skipped over these ones in the middle. These are called the transition metals. Okay, so these include things like iron, copper, nickel, and so on. These are common metals. They're in the transition metals. And we also glossed over these ones down the bottom there. They're sort of squeezed in where you see those flashing symbols. This would make the periodic table far too long, so usually they're cut out and put at the bottom instead. But we're going to focus on group 1. Here they are, group 1. Now, what do they have in common? This is the important point. What do all these things have in common? Well, to understand this, we need to look at the atomic structure. So, let's start off with the first atom, hydrogen. So hydrogen consists of a proton, and the proton is coloured red here. The proton has a positive charge, and this is balanced by the same number of electrons. The electrons are shown in yellow. So the electron is whizzing around the nucleus. The nucleus is made up of protons and neutrons. The hydrogen atom, though, doesn't usually have any neutrons. The number of neutrons varies. Neutrons have no charge, but we can have different numbers in the same sort of atoms. So we're really interested in the number of protons and electrons. Now, as we move across the periodic table, from one element to the next, the number of electrons and protons increases by 1. We add 1 extra proton, positive charge, in the nucleus, and 1 extra electron to keep it neutral. So here, this is helium. We've got 1 extra electron. Now, the next key point is that we start adding electrons into different shells. So for the next element, lithium, with 3 electrons in total, it has just 1 electron in its outermost shell, moving around, as you see, moving around right around the far away from the central nucleus. But then we move across again, we add an extra proton, an extra electron, so beryllium here in group 2 has 2 electrons in its outermost shell. Boron has 3 electrons in its outermost shell. Carbon here has 4. Nitrogen has 5 electrons. Oxygen has 6 electrons in its outermost shell. Fluorine has 7 electrons in its outermost shell. There's 2 in the middle as well, so there's 9 in total, but 7 in the outermost shell. Neon has 8 in the outermost shell, and that's full up now. So now the next electron that we have to add goes into a new shell, and this is where we get back to sodium, the next one in group 1. So now, this is where we do a bit of sky at night. If we can have the lights down, please. I'm going to point out all the alkali metals, or the group 1 metals. We have them hovering above you. So hydrogen is here. This is hydrogen. And it's only got 1 electron, of course, and here is its 1 electron moving around. We can see they're all lit up. So this is hydrogen. Next, we go to lithium. Well, lithium is shown up here. And again, this has one electron in its outermost shell. Okay? This is what all of the elements in group 1 have in common. They all have one electron in their outermost shell. Sodium is shown at the back here, and there is its outermost electron, one electron again in its outermost shell. This is what we see on the screen here as well. Sodium with its single electron in the outermost shell. The next element is potassium, and again, this has many more electrons, many more protons, many more neutrons in the nucleus there, but again, one electron in its outermost shell. Potassium is shown over there, okay, and there is its outermost electron, all by itself. Next element, what do we come to after potassium? We come to rubidium, and again, one electron in its outermost shell. Rubidium is shown up here. And there is its electron, okay? One electron in its outermost shell. Finally then, we get to the largest member. Look at all these neutrons and protons in the nucleus here. Many, many neutrons and protons in the nucleus. And this gives it all its mass. It's very heavy indeed. Many, many electrons, but still just one outermost one. And this is the important thing. All of the group 1 elements have one electron in their outermost shell. And here's our cesium, and there's its outermost electron moving around on the atom up here. So this is the important thing. One other thing that's rather interesting, actually, is the scale of these atoms. We've shown all the electrons rather clustered around the nucleus here, but actually these electrons are much further spaced out. The nucleus makes up all the mass of the atom, so it's all concentrated in the heart of the atom, but these electrons are really spread out. And if they're on this sort of scale that you see here, these electrons should be up to around 1 kilometer away from the nucleus here. So the vast majority of the atom is actually empty space, and the electrons are moving around that space. But these atoms, these group 1 atoms, are actually the largest atoms in the periodic table. Cesium is the largest atom there is. Okay. There is actually one other element in group 1, and this is the one right at the bottom here, francium. This is even bigger. So the heart of the atom there, the nucleus there, is really rather large. And we have a francium atom here, but the thing about francium is it's radioactive, and this means that bits drop off, and then it's no longer a francium atom. So we don't really need to worry too much about francium. I couldn't have any francium here in the lecture theatre because it would disappear very quickly. In fact, if we did have a block, here's a block, look at that. So if we think that's one big block of francium here, look how big it is, well, it gradually decays. Now, we've set this up to decay at exactly the right rate. So if you look at the top, there we are, it's decaying away. And the rate at which it decays, well, after 22 minutes, it's decreased by half. So keep an eye on that during the lecture, and you'll see that it gradually just disappears. So in 22 minutes' time, there's going to be half the amount that there is now. And 22 minutes after that, it's decreased by half again. Then 22 minutes after that, half again. And this is called the half-life. So francium has a half-life of 22 minutes. Okay, so we won't be doing any experiments with francium. And actually, it turns out that cesium is the most interesting element anyway. It's by far the most reactive. It is actually even more reactive than francium would be. Okay? But I won't go into why that is, unfortunately. You need to understand some relativity for that. Okay, now, the key thing about all of these elements then that we're looking at is that they have one electron in their outermost shell. And chemistry is all about electrons. We can excite these electrons, or we can share them and move them around from one atom to another. Okay, now, what we have here is a sodium street lamp. Very bright indeed, and you've of course seen this. This is used to light up our streets at night. Incredible yellow colour here. But why is this yellow? Well, if we take a normal lamp, this is a normal filament lamp, and we split up all the colours that come out from this, what we would see is the spectrum, a rainbow of all the colours like we see on the screen here. So we have a lamp, and we're actually shining the lamp just on the corner of a DVD, and this is splitting it all up into the colours of the spectrum. So this is normal white light. If I move my little camera now that we have here, so here's the little camera, there's you, move the camera and put it into onto this one, we don't see a complete spectrum here. What we actually see are discrete lines. So only certain colours are coming out of this lamp. This lamp contains a number of different atoms. It actually contains some mercury and cadmium and zinc. It's a calibration lamp here because it has quite a lot of these lines. But the lines that we see are unique to every atom. It's like each atom has its own rainbow barcode that's unique to every atom. And we can actually work out what the atoms are by looking at the exact colours that are given. So here are the colours that are given by the group 1 metals, if we split up the light from these. We see, for instance, that sodium has just one very, very bright yellow line there. It's actually, if we look really close, we see that it's two very closely spaced ones. But that really dominates, and this is what we're seeing here. Other elements have their own unique colours. This potassium is often described as sort of lilac-y colour, and this is a rubidium lamp here, a rather purple colour. Well, what's the origin of these? Where does the colour come from? Here is our sodium atom. I've only taken just the outermost electron. We've forgotten about all the other ones just to keep things simple here. And we're going to give this some energy. So here's some energy here. We have some energy, going to give it some energy, and look what happens to the electron. The electron gets really excited now. We've given it some energy, and it's gone to a higher energy level. So here it is, very, very excited. But then it goes back to its normal state and gives out that energy. So it's returned to normal now, giving out that energy in the form of light. And that's what's taking place here in the sodium street lamp. OK, so we've seen the lamps here. And we can see that sodium is certainly very useful for lighting our streets, but rubidium really wouldn't be with this rather purple colour. But let's see this in practice now with some chemistry. So we're going to do exactly the same thing now chemically. So the letters at the back here are soaked in compounds containing the real elements. So here's the symbol for cesium, and we've soaked this in cesium salts. Here's rubidium, soaked in rubidium salts. Potassium. Here's sodium, the same yellow colour that we saw from the street lamp, and here is lithium. So the colours that you're seeing are due to electrons being excited, and each element has its own particular unique colour there. So chemistry is all about electrons. Sharing electrons, promoting electrons, and so on. This is what we're seeing here. Well, we can it's even possible to, well, almost see some electrons. This is liquid ammonia in a special piece of apparatus so we can keep the liquid ammonia from boiling off. And I'm going to add some sodium to this. So I have some sodium here. I'm going to add this into the ammonia. OK, and you should be able to see on the camera here where the sodium is reacting in the ammonia here, and we're getting a blue colour. And what's taking place here, the electron is coming away from the sodium metal, and it's just staying in the solution, in the ammonia. And the blue solution that's resulting, we're beginning to see a little bit of the blue solution forming here, is due to the free electron moving around in the ammonia. This is a solvated electron. So we're forming sodium ions, Na+, and we're losing this outermost electron, and this is giving rise to the blue colour that we're seeing. It should eventually turn into a really deep blue colour all through this solution. So just keep it, you can certainly see it at the bottom here now, all the wisps of colour coming off of this. So just keep an eye on that, and you should see it all goes completely blue after a short time. So there we're allowing the electron to come away. This is this outermost electron, and it doesn't matter which metal we're using here. Any of these would give rise to this same blue colour, thought to be a solvated electron moving around in the ammonia there. But what do the elements actually look like themselves? So let's have a look at the group 1 metals. Well, here is lithium. So it's a solid. It's a metal. It looks slightly sort of black some parts here, but the rest of it is sort of silvery coloured, typical metal. So there's lithium. We have some sodium here. So here is some sodium, again, very shiny metal. We have potassium, here's some potassium. Again, just a shiny silvery metal. And here is rubidium, this rubidium in the bottom of the tube here. Again, another shiny metal. And finally, we have some cesium, and Chris has been keeping this nice and warm by holding it, and it's actually melted. Okay? So this really is quite beautiful. It's like liquid gold. This is a golden coloured, so it's still a metal, but actually it melts just above room temperature. So just by holding it, we can see it turn to a liquid. Okay, so this is cesium metal. So that's what they look like. They're all metals, okay, all shiny metals. Well, all apart from one. The one at the top of the group is not a metal at all. This is the one at the top of the group. This is hydrogen. And of course, hydrogen isn't a metal, it's a gas. Okay, so very different indeed. But on this planet, and this is the planet Jupiter, well, Jupiter is mainly made up of hydrogen, and it's thought that in the center of Jupiter, under all the pressure there, the hydrogen that there is squashed and squashed and squashed, and initially we get solid hydrogen, but if we keep squashing it, we end up with metallic hydrogen. So Jupiter is thought to consist of a metallic core. So right in the heart of this is metallic hydrogen. Now, it's very, very difficult to get these pressures here on Earth, but it has been done in one experiment. They managed to squash hydrogen enough using a diamond anvil, and then they measured the conductivity, and it turns out to be pretty much the same as the other group 1 elements. So hydrogen, yes, is very different, but under the right circumstances, maybe it's possible to get it to be just like a metal as well. Okay, now what about the reactions? Well, interestingly enough, just mixing up the metals, with the exception of lithium. Lithium is slightly unusual. It is a little bit different from the other group 1 metals. It has a, can I find a left glove, please? Rather than 2 right ones, thank you. Thank you very much. Lithium is a little bit unusual. It has the highest melting point of all of the group 1 metals. But apart from lithium, all of the others mix together very, very easily. Now, what we've got here is a tube containing some potassium and some sodium. There's lots of chunks here. And all we've done here is just squash them together. So literally just pound them together a little bit for about 5 minutes, and it turns into a liquid. Now, we can see this. I should be able to suck up some of this alloy, this mixture of the 2 metals of sodium and potassium. We're just going to do this under an argon atmosphere, so Mark is just adding some argon gas because it will react with the oxygen. But here you can see this is now a liquid, and it goes back down again. So I've just made it drop out. It clings to the glass quite a bit though, but this is now liquid metal formed just by mixing the sodium and the potassium together. So all of the metals mix together pretty easily, with the exception of the lithium. You need to get to very high temperatures before that does mix with the others. But what about hydrogen? Well, hydrogen reacts with the metals. We can have show the chemical equation for this. We have lithium reacting with hydrogen, and it forms lithium hydride. Similarly, sodium reacts with hydrogen, and it forms sodium hydride. In all these reactions, every reaction that you're going to see, if we're starting with the metal, during the reaction, the metal loses its one outermost electron and so forms a positive ion. So here we started off with neutral sodium, Na, and we're ending up with Na+. And in this case, it's given the electron to hydrogen and formed the hydride ion. So this is a chemical reaction now, where sodium here combines with hydrogen. Well, I can show you the properties of sodium hydride. We have some in a tube here. Sodium hydride is a fine powder, very, very reactive, and watch what happens as soon as it comes into contact with water. So we have a tray of water here, and I'm just going to blow some sodium hydride onto the water. As soon as it comes into contact, it reacts. Well, what's the chemical equation taking place there? Look at the reaction here. We have our sodium hydride reacting with water, and it's forming sodium hydroxide and hydrogen gas. Now, Could that reaction be at all useful? Well, it could be useful. It could be a means of providing hydrogen gas. And in fact, there was a taxi in London a few years back that was run off of hydrogen gas generated by the reaction of sodium hydride with water. So this could be used as a means of storing hydrogen gas. Hydrogen is very, very flammable, and so how are we going to store it? We could compress it, but then we'd be having cylinders of hydrogen gas. Well, one method that was suggested was using sodium hydride. So Mark is going to add some sodium hydride. It's all wrapped up in a gauze. So this should sink to the bottom of the beaker here before it reacts on the surface. There we are, lovely. So this is now sunk to the bottom. Bubbles are forming, and this is the hydrogen gas. So remember, sodium hydride reacts with water to form hydrogen gas. And the hydrogen gas is, of course, flammable. There we are. So just generate a few more. And so as I say, this was actually used to power a taxi using the hydrogen gas here as the fuel. It's a clean, environmentally friendly fuel because when it burns, all we get is water. But this brings me on to the next point. And this is that we don't find any of this family occurring naturally in nature. We don't find hydrogen in the air. Well, why not? It's because, of course, hydrogen is very flammable. It burns in the air. Oh, like that. Okay. So the reaction that's taking place there is, of course, hydrogen reacting with oxygen to form hydrogen oxide or water. Well, similarly, all of the metals in group 1 also react with the air. Thank you. I have some lithium floating on some mineral oil, and the oil here is to protect the lithium from the air. But even so, there's a very black crust on the surface of the lithium, and this is actually lithium nitride. So the lithium actually reacts with nitrogen gas. If I cut it, and it's sort of rather hard to cut, but I can cut it with a knife here. There we are. It's pretty hard. And you see that initially it's very, very shiny. Well, this shiny surface of the lithium will eventually tarnish and go black. In fact, it's beginning to change already. And this is as it's reacting with the gases in the air. So let's see if we can get this lithium to react with the gases in the air. I'm going to heat up some lithium. So let's take the little piece here. Okay, and I'm going to heat it in the flame here. And if we have the lights down, please. Now you may see the crimson colour of the lithium. There's just a little bit there around the flame. So that, remember, the crimson colour is unique to lithium there, this exact shade of crimson. But now the lithium is, there we are, it's burning in the air, reacting with the air, and it can burn, combines with either the nitrogen or the oxygen of the air. Okay. So this is the chemical equation that's taking place. Lithium can combine with nitrogen from the air to form a compound called lithium nitride. And this has 1 nitrogen ion and 3 lithium ions. So the lithium, remember, it loses its electron in every reaction, forming lithium plus, and the nitrogen is capturing the electrons. So this is essentially what we have. We have 1 nitrogen with 3 lithiums around it. This is lithium nitride. Okay. Well, could lithium nitride be of any use? Well, I have some lithium nitride in the tube at the back here. So you should be able to see the brown, dark brown sort of solid here. This is the lithium nitride. And at the moment, it's under an atmosphere of hydrogen. So I'm going to try and heat this very carefully without the hydrogen catching fire. And we should see, well, of course, when you're heating up all the air inside here, all the gases, we should expect the balloon to get bigger. There we are. And now I can begin to see a reaction taking place. And the brown lithium nitride is turning white. And the balloon is actually going down. Okay, the balloon is going down. And this is because it's absorbed, it's reacting, the hydrogen gas is reacting with the lithium nitride. Okay, so a reaction has taken place here. We've now got a white solid in here. This is lithium amide. Here's the chemical equation for what's taking place. We have the lithium nitride, Li3, 3 lithiums to 1 nitrogen there. Lithium nitride reacting with hydrogen to form lithium amide. So some of the hydrogen is now incorporated onto the nitrogen there, and also forming lithium hydride. But if we heat this up even stronger, this hydrogen is released again. So this has recently been proposed in the last 10 years as another means of storing hydrogen gas. Because if we heat up the lithium nitride, it absorbs the hydrogen, then heat it up still higher temperatures, the hydrogen comes out again. So maybe this is also a means of storing hydrogen as a fuel. So that's lithium nitride. This is the reaction where lithium combines with nitrogen. But lithium also, when it burns, we saw it burning very brightly, the white flame there, well, that was really probably due to the reaction of lithium metal with oxygen. So here's the chemical equation for this, lithium reacting with oxygen to form lithium oxide. Well, it's very difficult to show some of these reactions. In fact, we started off thinking it would be nice to show the reaction lithium combining with nitrogen under just nitrogen gas and lithium combining with oxygen under pure oxygen gas. But it's all really complicated by the fact that actually lithium reacts with glass. And so in order to see the reaction, okay, it was very, very difficult to do this because actually the lithium was just reacting with the glass. So we thought we'd show you this reaction, how lithium can combine with glass. In the tube here, we have lithium solid in the bottom, in the test tube here, and powdered glass. And I'm just going to heat up the tube. Now this will take just a couple of minutes to get going. So this is lithium mixed up with glass. And perhaps if we have the lights down for this as well, please. So you can see when the reaction starts, since we get a bit of a red glow. Okay, and I think it's almost starting at the bottom. There we are. Okay, and that you can see it glowing red hot. This is the lithium combining with the glass. Very, very violent reaction now. And what's happening here, the lithium is stealing the oxygen from the glass itself. Usually glass is very, very inert, doesn't react with things at all, but here this metal is taking the oxygen away from the glass, and the black colour that you're seeing left behind consists of silicon, which is part of the glass there. Silicon oxides make up the glass. So you can still see that it's glowing red hot. So this is the reaction of lithium and glass. Okay, well, that's lithium. Let's have a look at the next element now. Well, sodium. Sodium doesn't combine with nitrogen. It doesn't burn in nitrogen. It doesn't react with the nitrogen from the air. But it is possible to make a compound between sodium and nitrogen, just not by combining them directly. Okay? So it is possible to make a compound, and this compound is very, very different. Before, we saw the lithium nitride, and this had the chemical formula. It was Li3N. So there were 3 lithiums and 1 nitrogen. Well, the compound that we can make between sodium and nitrogen, not by directly combining the elements though, but the compound that we can get is called sodium azide, and this has 1 sodium and 3 nitrogens. So this is the structure there. All the nitrogens, the 3 nitrogens are in a row, so there's a unit of 3 nitrogens there with 1 overall negative charge, and the sodium, as usual, has lost its electron. It's given them to the nitrogens there to form a positive ion, sodium plus. Sodium azide. Well, watch what happens when we heat up some sodium azide. So in the tube here, we have a small quantity of sodium azide, and this is a white solid, so this is in the bottom of the tube. I'm going to heat this up. This is just to make sure that no gases come backwards, no water comes into the apparatus here, but we will be collecting any gases that are formed by displacing the water in this tube. So I'm just going to heat up the sodium azide. So just warming it, and you can see that maybe it's just because the air is expanding, a few bubbles have come up. Just keep on heating. Oh, and all of a sudden, look at the gas that's been formed. We're seeing a black color forming in the tube here. The black colour is actually due to metallic sodium, and the gas that's forming over here is nitrogen gas. So what's taken place here, the sodium azide has decomposed to form sodium, and that's the black colour that you're seeing here. We've got metallic sodium, pure sodium. Maybe it's beginning to react with the glass, okay? But we're also forming nitrogen gas. This reaction has been responsible for saving thousands of lives, and Chris will show us how. So here comes Chris, and with his little car here, well, this contains some sodium azide. The sodium azide is in the steering wheel. It's in the airbag. Okay? The airbag contains sodium azide. And under the right circumstances, we can trigger the rapid release of that nitrogen gas to form sodium and nitrogen. The sodium then reacts further with other chemicals that are added in there. It actually contains essentially sand to react with the sodium. The sodium steals the oxygen from that in the way that we've seen with the glass. But this produces a lot of nitrogen gas very, very quickly. So are you ready for this then, Chris? Okay, we'll have a countdown from 3. Don't blink, otherwise you'll miss it. This is the decomposition of sodium azide to initially form sodium and lots of nitrogen gas. So 3, 2, 1. There we are. And you see, Panda is perfectly safe. Yes. Okay, of course, now that sounds very loud, but believe me, apparently, if you're unfortunate enough to actually have one of these things go off, the last thing you're worried about is the noise from the airbag. Okay, but as I say, this has saved many, many lives. It needs to go off incredibly quickly, so actually, when you hit the airbag, it's not blowing up, it's actually going down again, it's deflating, so you have a nice soft landing on your airbag. So that's the compound formed between sodium and nitrogen. But as I say, we can't make this simply by combining sodium with nitrogen. Quite the reverse. We see that it decomposes on warming to reform the sodium and releasing this nitrogen gas. Okay, so what else can the sodium react with in air? So if we cut sodium, we should be able to see a reaction. Here is the sodium, and at the moment it looks, well, rather sort of white. But again, if I cut this, I'm just going to chop this using the knife. It's much easier to cut than the lithium. And it is, well, initially at least, it's very, very shiny indeed. But already it's beginning to tarnish. So the shiny colour is getting dull. It's becoming dull already. And this is as the sodium is reacting with the gases in the air. Not the nitrogen, only lithium can combine with nitrogen. This is reacting with the oxygen and possibly with any water vapour that may be there. But this is forming sodium oxides. The chemical equation for the reaction is sodium combining with oxygen to form sodium oxide. And the formula for sodium oxide, just like with the lithium oxide, is Na2O. So 2 sodiums and 1 oxygen. But if we burn sodium with lots of oxygen, we can actually get a different compound formed. And this is called sodium peroxide. So this has much more oxygen built into its structure. So normal sodium oxide had the formula Na2O. Sodium peroxide has the formula Na2O2. So this is the structure for sodium oxide. Each sodium has lost its electron to give us the Na plus ion. This is counterbalanced now by 1 oxygen in sodium oxide, so we have an O with double negative charge. But in sodium peroxide, we have 2 oxygens still joined together. Overall, they have a double negative charge, so if you like, 1 negative charge each. But now we have the 2 sodiums and 2 oxygens in the peroxide unit. Okay. Well, what can we do with sodium peroxide? Well, with all this extra oxygen, it turns out to be rather reactive. We can release some of this oxygen, and we can get it to combine with things. So what can I get it to combine with? How about some Rice Krispies? Now, of course, we get our energy by the combination of oxygen with our food, such as our Rice Krispies. So we're going to show exactly that same reaction now. So this is our food, Rice Krispies. Add some oxygen, and the oxygen here is in the form of sodium peroxide. So this is a nice yellow powder. So I'm going to sprinkle this on just like I would sprinkle my sugar on. Maybe that was a little bit too much sugar. Okay, and then, well, you'd add your milk. Well, I'm not going to add milk, I'm going to add some water. And perhaps if we have the lights down. Now, added the water allows the peroxide to come into contact with the Rice Krispies, and look at all the energy that's released. So there's a lot of energy now that's released, and this is as the Rice Krispies burn with the oxygen supplied from the sodium peroxide. So the peroxide had lots of oxygen available to it to react. Okay. So that's sodium. Well, let's now have a look at potassium. So this looks sort of rather black at the moment, this potassium. But let me cut this. And now it's getting really easy to chop. This is very soft indeed. But as soon as I've chopped it, well, it did go very bright and shiny initially, but again, it's already tarnished. So it's even more reactive. As we're going down the group, the family group, the metals are getting more and more reactive. What oxides can we get? Well, we can also get the potassium oxide, the same as before, K2O. We can also get the peroxide with a bit more oxygen. But with excess oxygen, we can get another compound. And this compound is called potassium superoxide. So it's got even more oxygen in it. Okay? Potassium superoxide. So this has one potassium ion. So again, the potassium has given up its electron. But now this has given up its electron to just a normal molecule of oxygen, O2. So we actually have O2 with one negative charge shared out over both of the oxygens. So this is the structure here, the unit that we have in potassium superoxide. So one potassium to two oxygens. Well, this is very reactive indeed. Now let's have a look at some of the reactions here. I have some potassium superoxide in this tube. So it's a beautiful yellow colour. And I'm going to add some water. Bubbles form, and a gas is given out. This gas relights my glowing splint. This gas is oxygen. So as soon as water comes into contact with the potassium superoxide, it rapidly forms oxygen gas. Here's the chemical equation for this. We have potassium superoxide reacting with water to instantly form oxygen and potassium hydroxide. But this reaction is also incredibly useful, as Chris will demonstrate. Come on, Chris. Okay, Chris is now modelling the latest in breathing apparatus. This breathing unit here contains potassium superoxide. So this is the unit that has potassium superoxide in it. You can just about see the yellow colour in this. This is located here and over here. And so what happens? As Chris breathes, breathe. Yes, as he's breathing here, of course, he's breathing out water vapour in the breath. The water combines with the potassium superoxide and liberates oxygen gas. So this is allowing him to stay alive, which is a good thing. But also, of course, Chris is breathing out carbon dioxide, and this is actually very bad. And this leads to if we don't remove this carbon dioxide, we begin to choke very, very quickly. So we need to get rid of the carbon dioxide. Now, the equation here, the potassium superoxide reacts with water vapour to form oxygen, which is good, so we can breathe that to stay alive, but it also forms potassium hydroxide. And the hydroxide reacts with carbon dioxide to form potassium carbonate. So not only does this give more oxygen for Chris to breathe, it also removes the carbon dioxide. So it's a very clever piece of kit. So this is called a rebreather because it allows Chris to carry on rebreathing the same air, just replenishing the oxygen using the potassium superoxide here. So this is used for sort of emergency situations where a source of oxygen is required. But there is no cylinder, there's no oxygen cylinder here, it's just the potassium superoxide supplying the oxygen. Thank you very much. Good. Okay, so that is potassium. Now, I was thinking, well, what could we get our potassium superoxide to react with? We've seen it reacting with water, but it should be able to, it's got all this oxygen, surplus of oxygen, what could it react with? And when I was putting the lecture together, I thought, well, what should we have it react with? And there's all sorts of different possibilities. I thought, well, what would be nice would be to have it react with one of the other alkali metals, one of the other group 1 metals. So, of course, lithium really wants oxygen. Potassium superoxide has more than enough oxygen to spare. So maybe if we mix the two together, we should be able to get a nice reaction. Okay, this is the potassium superoxide, the yellow potassium superoxide added to the lithium. Okay, I think I'll just give this a bit of a stir. Just make sure they're all nicely mixed up together. Now, when we tried this, I didn't know whether this was going to work. I thought, well, it ought to. I mean, chemistry says that, say, the lithium wants lots of oxygen. The potassium has more than enough to spare here, so it ought to react. We just give it a drop of water. So in the same way we started the reaction with the Rice Krispies and the sodium peroxide, we can start this reaction with a drop of water. It just allows everything to mix nicely. So add a drop. There we are. And if we have the lights down, please, maybe we can see a reaction take place here. Well, it's caught fire. That's a good sign. And the lithium is now burning in the oxygen produced by the potassium superoxide. So this brilliant white light is the lithium here reacting very, very quickly, very vigorously with the oxygen. So a very violent reaction. Actually, when we first tried this, we accidentally destroyed the fume cupboard. Involved lots of paperwork, yes. So we've scaled it down a little bit here. But there we are, okay. Well, of course, there are 2 metals left. Now, I have a sample of rubidium, and at the moment it's kept under argon gas, and it's on the glass at the bottom here. So it does not react with argon at all, and this is keeping it hopefully safe from the air. But watch what happens as soon as I take the lid off of this. As soon as I take it off, it's gone crusty, it's gone white, very, very quickly indeed. If I just sort of tap this about a bit, it sort of melts, it's reacting very quickly, and little sparks are coming off. We have the lights down, please. You might be able to see some of the sparks coming off. There we are. Okay, this is reacting violently with the oxygen from the air. As soon as it comes into contact with air, very, very violent. So rubidium is even more reactive than potassium. And of course, the final group member is cesium. And you can see maybe, hopefully on the camera there, that this is actually liquid, because it's rather warm at the moment. So this is liquid, and again, I'm going to take the lid off. Oh, and as soon as I take it off, a little spark came out. And again, if we have the lights down, maybe we can see if there's anything left. Oh, there's a little spark there forming. Okay. It's essentially all reacted. It's gone already. So again, very, very reactive. This is the most reactive of all the metals. So there is no cesium left now, just this black oxide. Okay. Right, so this is why we don't find these metals in nature. They are so reactive. But of course, it's not just the air that they could react with. There are other things as well. It could also react with the water. And this is what we're going to show now. The way you may have seen this in previous demonstrations, they normally throw the metal into some water. But there's all sorts of problems with this, because the metal may have grease on it. It may be contained in a glass ampule if it's a really reactive metal like cesium or rubidium. So we're going to do this rather differently. We're going to add the water to the metal. Okay? We're going to use the same quantity of metal every time. And not the same mass, but the same number of atoms. So Mark has very carefully counted out the number of atoms, and he's got the same amount each time. So we're going to start off with lithium, and I'm going to add the same quantity of water every time as well. We're going to add 10 mils of water to our metal. So I'm going to take the top off. At the moment, they're under argon. So there's no reaction of the metal with the air. Argon is heavier than air, and it's just sitting in the tube protecting the metal from the air. And we're just going to add some water. So this is lithium. You can see that it's bubbling rather nicely. It's forming hydrogen gas. And in fact, we can see the chemical equation for the reaction. It's the same chemical equation for all of the elements. We have the metal reacting with water to form the metal hydroxide and releasing hydrogen gas. So every time it's the same equation. But what we're trying to do now is see if we can tell the difference between the reactivities of the different metals. So out with the lithium, in with the sodium. Now again, it's the same quantity of metal, but does it react any more vigorously? I'm going to add the same quantity of water. All right, so the sodium, certainly a lot more violent than the lithium. In fact, it caught fire. Notice the yellow colour. This is the colour characteristic of excited sodium atoms. So the sodium was clearly having a good time there. Right, potassium. Again, the same quantity, the same number of atoms. We're trying to keep everything as controlled as possible. The same quantity of water. Just as an added safety precaution, I think I'll put this on. Right, so potassium now, and water. Getting more vigorous. Okay, maybe we can, yes, that's a good idea. We'll just remove some of the smoke so you can see the next one more clearly. Now some rubidium. We had an extra blanket, I think. Here's the rubidium in the tube here. We can see the rubidium metal under a blanket of argon. And again, it's exactly the same quantity. Every time we're using the same quantity. This is now rubidium, same quantity of water. Beautiful blue colour. That's the colour of the rubidium flame, remember. We need to wait for that to go. Okay, we'll just wait for this to clear because this is a one-off experiment here. The amount of cesium that we're using is 5 grams, and it costs several £100s. So here is our cesium. And again, if we just show this on the camera there. So there's quite a bit of the metal down in the bottom of the tube, and again, it's under a blanket of argon. Okay, so it will not react with argon gas. When I take the stopper off, it will not be reacting with the air because the argon is heavier than air. And so that will protect it until it comes into contact with the water. And we've used the same quantity of every metal here, the same number of atoms. Okay. Here is our water. And there we go. Not bad. Oh, I'm pleased that one's over. Good. Right. So actually cesium, though, I mean, it is the most reactive. There's no doubt. It's the most reactive of all of the metals and reacts very, very quickly. It's also heavier than water. Both rubidium and cesium sink to the bottom of water. So that's one of the reasons it reacts very quickly. But I always think that the best reaction, actually, is with sodium and water. This is my favourite, because I think the sodium has more of a chance to sort of build up the tension and heat up. It's much more interesting. So we're going to try some more sodium now on a slightly larger scale in the tank here. Okay. Notice the amount of francium left. It's still decreasing. There's not a lot left now. So that's why we're not going to be looking at any francium. Okay, here is our sodium. Going to drop this into the tank and run away. Okay. Can't see where it is. Oh! There we go. Nearly coming to an end. So these metals are obviously clearly very, very reactive. They react with the air, they react with water. So how can we find them? Well, we can find them in various minerals. This is the mineral where we get our sodium from. This is sodium chloride. Okay? And of course, we can find sodium chloride. Well, where do we find sodium chloride? Salt. And where do we find lots of salt? In the sea, yes. And this is a picture of me. I was lucky enough to be invited to give a lecture in Israel. So here I am not giving the lecture in Israel. I'm floating on the Dead Sea. But of course, it's very easy to float on the Dead Sea because it's so dense with all the salt water in there. But putting the lecture together, I thought, well, okay, everyone knows about sodium chloride, and it's very, very dense, and it's easy for people to float on it. But what would it be like if the sea was made of cesium chloride instead? Okay. Now, I thought it'd be really nice to actually float on the surface of some cesium chloride. And we were looking into getting a nice big tank full of cesium chloride for me to float on top of. But unfortunately, some American lawyers said that wasn't a good idea. And they stopped us, which is a bit of a shame, really. So instead, I'm going to show you something else. And this is a block of metal. This is solid metal. It really is. I mean, it weighs 8 kilos. And it's a block of magnesium. Magnesium sinks, not surprisingly, in water. It sinks in seawater. Okay? It would sink in the Dead Sea. It's quite dense. But if the sea was made of cesium chloride instead of sodium chloride, we'll see how long it takes to sink in the cesium chloride. So here I'm going to drop it in, I'm going to release it now, and you watch how long it takes to get to the bottom. It doesn't. It floats. Okay, so this is an 8 kilo block, solid block of metal, floating on cesium salt dissolved in water. Okay, this solution here, well, could this have any uses? Indeed it does. This was supplied by a company who sell it to oil companies, and they use it in the drilling process. They pump down some cesium salts, and this helps little particles of rock come to the surface more easily because, of course, it's so dense. But it's an environmentally friendly solution. It isn't poisonous. It would be relatively safe to float in it, honest. But, yep, so there we are. Even this has a use, which is fantastic. So, how do we get our cesium, then? This also comes as a mineral. And I have some cesium mineral here. This is pollucite. This is the mineral containing cesium. So we have a number of different minerals. We have our sodium chloride. This contains sodium and chlorine ions. So we have sodium ions. These, remember, sodium wants to give up its electron, its outermost electron, to form Na+. These are the Na+ ions. And in the sodium chloride structure, every alternate atom here is a chloride ion. This chlorine has grabbed the electron. So we have Na+, Cl-, Na+, Cl-. Well, unfortunately, I couldn't show you the process where sodium and chlorine combine because the chlorine is so poisonous. We did a quick video. Maybe we can show you this. Here's the chlorine cylinder. So we're about to pass the chlorine. This is a green gas over some sodium. Here's the sodium here. We recorded this the other day in the fume cupboard. Going to heat this up. So here we are, heating it up now with a Bunsen flame. And the chlorine gas is just about to come over. You can see the yellowy colour there, the gas going over the sodium. And after a while, the sodium will catch fire. So you should see the brilliant yellow colour that we get. So any second, we should see the brilliant yellow colour. There we are. This is the light coming out as the sodium and the chlorine react. Gives out a lot of energy, heat energy, light energy. The yellow colour is, of course, the yellow of sodium. And what are we getting at the end of the day? We are forming sodium chloride. You shall see in a moment when we see the tube, there's actually a lot of black around the tube. And this is where some of the sodium has actually reacted with the glass. Remember, these metals are so reactive, they react with the glass. But also, we see the white colour here. That is sodium chloride. And we can see this in this last shot here, the sodium chloride. This is just our normal salt that we would have on our chips. Here we are, crystals of salt formed from the reaction between sodium and chlorine. So I can't show you that one live, but I can show you a related reaction, not using sodium, but using potassium, which is in the same group, of course, as sodium, and not using chlorine, but using iodine. These two react. Iodine is also in the same group as chlorine. These two also react to produce a structure exactly the same as the sodium chloride. Potassium reacts with iodine to form potassium iodide. But in this case, the iodine, unlike the chlorine, is a solid. So it's a little bit more easy for us to show this reaction. We don't have lots of poisonous chlorine gas going everywhere. So we have some iodine here. This is solid iodine. There it is on the tray. Here is our chunk of potassium. Put this just to one side. I shall get my big glass rod here and just encourage the two to come together. Now, again, this one's a little bit unpredictable. It needs a bit of encouragement. So I'm just going to sort of mush them in a bit, make sure they're all nicely coated. So this is coating the potassium here with iodine. Oh, and there we go. Very violent reaction. And notice the lilac colour, the flame that we saw there, characteristic of potassium. That was iodine reacting with potassium to form a salt, potassium iodide. So what about the uses of these elements? Well, of course, salt, sodium in the form of salt here, very useful to us. We put it on the roads, but it's used in many different chemical processes. Similarly, sodium hydroxide, very, very useful. What about the other metals? Well, this is lithium. Early in the first half of the 20th century, it was possible to buy 7-Up, and the very first formulation of 7-Up had lithium in it. It was lithiated 7-Up, okay? And there were other drinks available, such as this one, Happy Day. Well, it was noticed that these lithium drinks actually were important in helping with antidepressant. So it acts as an antidepressant. And these are some lithium carbonate tablets. You see at the top there, lithium carbonate. This is used in the treatment for depression very successfully. Of course, lithium is also used in batteries. So all of your phones that you'll be using, this is a lithium battery from a phone, contains lithium. So very, very important. One of the advantages of lithium, of course, is that it's so light. We could also use some of the other alkali metals, some of the other group 1 metals, such as sodium, in making batteries as well. And, well, I'm going to show you a reaction here. This is a very large battery. In fact, the battery there is that entire building. This contains sodium and sulfur batteries. This one is outside Texas, and it's used to power a small city in Texas. So when all the power goes off, and there's no more supply coming from the national grid, they use this battery to light up the entire city. Okay, so this is an enormous battery, and this uses sodium and sulfur. Again, a very vigorous reaction that releases a lot of energy. Now, I can demonstrate this not to give electrical energy, that's done in a very controlled fashion, but just by mixing the metal and some sulfur. Now, in order to do this, I'm going to use the liquid metal that we made at the beginning of the lecture. This is the mixture of sodium and potassium. This is the alloy that we have in the tube here. So again, we're just going to open this under argon. Okay, now I have a tube full of liquid metal. I'm going to add this to the sulfur in the tank here. Okay, so far so good. Whew. Right. And then just give it a bit of a mix. Oh, here we go. Oh! Gets me every time. Oh. So, of course, the battery doesn't do that, but nonetheless, there's a lot of energy there to be released. It has a very, very high energy density, and it's incredibly efficient. So I hope then that you've seen that these group 1 metals are very, very reactive. Their reactivity is all due to this outermost electron that's very easily lost, and they have all sorts of uses. We saw the cesium, how, because it's so heavy, this is used in drilling, for instance, cesium salts. We've seen how many of the other metals, such as lithium and sodium, can be used in batteries to generate energy. But one of the reactions we've seen is the generation of hydrogen gas, which of course is the top of group 1, and we're going to go out with a bit of a bang now. So I thought, how can we combine what we've learnt? Well, we've seen that sodium hydride reacts with water to produce hydrogen gas. We've seen that potassium superoxide reacts with water to give us oxygen gas. Okay? So, well, maybe if we mix the two together, we get a mixture of hydrogen and oxygen, and that should go with a nice loud bang. Well, that's what we're going to try now. Now, I need to take one glove off because I need a finger to put in my ear. Okay, all right. So first of all, the sodium hydride. There we are. Hopefully that's going to sink. Yes, that's giving hydrogen gas. Now the potassium superoxide. So that's generating oxygen gas. Maybe it won't go bang yet. Well, let's see. Oh, well, not bad, but I'm sure we can get a louder one than that if we get them to mix properly. So let's apply a light now. If you don't like loud bangs, I do recommend putting your fingers in your ears. Okay, so this could get quite loud. Getting quite loud. I'm sure we can get louder than that. Okay, let's just wait for a few more bubbles to come here. So this is the mixture of hydrogen gas and oxygen gas mixed up in the right proportions. The hydrogen coming from sodium hydride, the oxygen coming from potassium superoxide. There's quite a few bubbles here now. Oh, yes, that's certainly quite loud. Are we going to get one more? Maybe one more bang out of this. Oh, we'll let them build up a bit, shall we? Yes. Yes, not quite enough yet. Nearly there. Well, let's give that one a go. Okay. Oops. Oh, yes, nearly there. Oh, okay. Well, I hope you've enjoyed the lecture. And there are many more activities taking place over Science Week, so do go and see what else is happening. And finally then, the last reaction of hydrogen with oxygen, just in case you missed the earlier balloon, perhaps we've got another one. Okay. So here we have the reaction of hydrogen with the oxygen from the air. Thank you very much indeed. Thank you.